This is chapter number 15, which is waves. We are talking about question and answer on waves. A string of mass 2.5 kg is under a tension of 200 Newton. The length of the stretched string is 20 meter. If the transverse jerk is struck at one end of the string, how long does the disturbance take to reach the other end? So what all is given to us? Mass is given, the tension is also given, the length of the string is given. We know that the mass per unit length is what? This mass divided by length. So this is mass per unit length. And we also know that the velocity of the transverse waves in the string is given by the relation V equal to under root T by mu. T is what? Tension. And mu we just found out. Just put it here. It will be 40 meter per second. Now, the time taken by the disturbance to reach the other end, we know speed equal to distance by time, so we have to find out the time. So we have to divide distance by speed, that is distance here in this case is L, the velocity we just found out, so L by V, this L by V, L is 20 and this meter, and then we divide it by 40, so it gives you 0.5 seconds. A stone dropped from the top of a tower of height is given. Height splashes into the water of a pond near the base of the tower. When is the splash heard at the top, given that the speed of the sound is this much? So what is happening here is from the top of the tower, a stone is being thrown and the voice is heard here. So height of the tower is given, the initial velocity, because it is starting from the rest, so we take u equal to 0, and the acceleration, of course, when it is dropping, it is gravity, it's 9.8 meter per second square. Then the speed of the sound in air is 340 meter per second. Now this T1, let us take T1 is the time from this point to this point, that is it is coming down, that is the stone which is striking the water in the pond. We can use the second equation of motion, that is S equal to U T1 plus half GT1 square. And when we put the values which are given to us, S is 300, initial velocity is 0, gravity 9.8, T1 we don't know. So T1 can be computed by this expression, 7.82. Now 7.82 is from this point to this point. Now the sound has to go back to here. Now this time taken by the sound to reach the top of the tower is what? The distance is again 300 only, and this is the speed of the sound. So 300 by 340, this is T2, this is T1, this is T2. So this is the first one is the time taken from here to here, second is the time taken for the sound to go from this point to this point, top of the tower, this is 0.88. We add these two, we get 8.7 seconds. A steel wire has a length of 12 meter and a mass 2.1 kg. What would be the tension in the wire so that the speed of transverse waves on the wire equals the speed of sound in dry air? The temperature is given and the speed is also given. So the length of the steel wire is what? 12 meter. The mass of the steel wire is 2.1 kg. The velocity of the transverse wave is also given. This is 343. The mass per unit length we have to find out. This is mu. This is mass per unit length. So mass you take per unit length divide by 12. So this gives you mass per unit length, that is 0.175 kg per meter. For a tension T, the velocity of transverse wave can be computed using V equal to under root T by M. So this is T by M, and if we want to find out this T, this is V square, we have to square it and multiply with mu. So V square into mu, because V is given to us, so we multiply this V square with mu, we just found out this mu, so multiply them, you get 2.06 into 10 to the power 4 Newton. Use the formula this to explain why the speed of the sound in air is independent of the pressure, increases with volume, increases with humidity. So the scenario is this V has gamma P and rho, pressure density gamma. So this density is what? Rho is given by mass by volume. We know that mass by volume, you can say mass is equal to density into volume. So M here is the molecular weight of the gas and V is the volume of the gas. So this equation becomes what? Let us put M by V here. So this becomes V equal to gamma PV by M. Now for ideal gas equation, if we have some N equal to 1, this PV equal to RT. We know that PV is equal to mu RT. We are stating that this mu is 1, number of moles. Let us take it as 1. So eventually this PV is constant if this temperature is constant, because P on the right hand side, this is universal gas constant. This T we are taking as constant. This is constant T. So PV will be constant. So both M, gamma, these are constant. We know that these values are always constant. So velocity will be what? If this is constant at constant temperature, gamma and M are also constant. So this velocity becomes constant value. So at constant temperature, the speed of the sound in gaseous medium is independent in the change of pressure. So if we have taken this relationship, and again for 1 mole, we'll again take this relation mu equal to 1. What is P? P is given by, P can be written as RT by V. Now again substituting this second in our first equation, that means this equation, we are putting RT by V in place of this P. So this becomes gamma RT by rho into V, and we know that rho into V, that is density into volume, is mass. So gamma RT by M. Here, because see, this mass will remain constant, rho into V. So what we get? Gamma RT. The gamma RT, gamma and R are also constant. These two are constant. So now we conclude from this that V is essentially directly proportional to the under root of temperature. The speed of sound in gas is directly proportional to the square root of the temperature of the gaseous medium. That means that the speed of sound increases. This increases with increase in temperature in gaseous medium. Let us take now Vm and Vd, V sub m and V sub b. These are the sound or speed of sound in moist air, and this is the dry air. So this rho m and rho d, these are the density of moist air, rho m, and this is the dry air. So let us take this relationship, this V equal to under root gamma P by rho. First, the speed of the sound in moist air. So let us replace this rho by rho m, and the speed of sound in dry air, we replace this rho by rho d. When we divide these two equations, this one and this one, when we divide these two, we get Vm by Vd, and most of the things gets cancelled. This is rho d by rho m. So you see that Vm is inversely proportional to rho m and Vd is inversely proportional to rho d. So the presence of water vapor will reduce the density. That is, this rho d is less than rho m, and when this rho d is less than rho m, we say this, because they are inversely proportional, Vm is greater than Vd. So the speed of sound in moist air is greater than its dry air. So in a gaseous medium, the speed of sound increases with humidity. You have learned that a traveling wave in one dimension is represented by this function, y equal to f x comma t. X and t, they must appear in certain combination, x minus vt, x plus vt. Now y equal to fx plus minus vt, this is given, is the converse true? Means is the if you backtrack it, is the reverse true? We have to examine these functions for y, which can possibly represent a traveling wave, all these. So first of all, the answer for this question is no. Then these are, they do not represent a wave. This do not represent a wave. This represent a wave, and this does not represent a wave. So the converse, we are saying that it is not true. What is the essential requirement? The essential requirement for a function, any function to represent a traveling wave, is that it should remain finite for all values of x and t. Okay, let us take the first one. For x equal to 0, you put x equal to 0 and t equal to 0. What will this will be? It will be 0. For x equal to 0 and t equal to 0, the function will represent a point. It is representing a point. It is not a wave. For x equal to 0 or t equal to 0, for this one, let us put x equal to 0, t equal to 0. You see, this becomes 0, and this log 0 is infinity. And since the function does not converge to a finite value at x equal to 0 and t equal to 0, it represents a traveling wave. For this one, x equal to 0 and t equal to 0, again it is 1 by 0, that is infinity. So since this function does not converge to a finite value for this x equal to 2, t equal to 0, it does not represent a traveling wave. I hope you got the idea. A bat emits ultrasonic sound of frequency this much, 1000 kilohertz in air. If the sound meets a water surface, what is the wavelength? First, of the reflected sound, second, the transmitted sound. The speed of the sound in air is given and water is also given. So here the frequency of the ultrasonic sound is 100 kilohertz, that is 10 to the power 6 hertz. Now what is the speed of sound in air, which is also given in the question? The speed, we know that V is equal to nu lambda. Nu is frequency, lambda is wavelength. So if we want to find out lambda, lambda will be V by nu, that is frequency. So this is V by nu. So the wavelength of the reflected sound is given by this, as I told you, this is V by nu. V is the velocity and nu is the frequency. This is the frequency. So what you get? Lambda. We got the lambda here. Now the frequency of ultrasonic sound, again velocity V will be, this frequency will be 1000 kilohertz, that is 10 to the power 6 hertz. And the speed of the sound in water, what will be this? This is given 1486. Again we will do the same thing here as we did here. So 1486, in this case we'll use V as 1486. 1486 by 10 to the power 6 is 1.49 into 10 to the power minus 3. So first case is this one, second case is this one. A hospital uses an ultrasonic scanner to locate tumors in the tissue. What is the wavelength of sound in the tissue in which the speed of sound is 1.7 kilometer per second? The operating frequency of scanner is this much. So what all is given? The speed of the sound in tissue is given like this. We'll convert this kilometer into meter. It will be 1.7 into 10 to the power 3. The operating frequency of the scanner is this much. This is in megahertz. Convert into hertz multiplied with 10 to the power 6. Now when we know that V equal to nu lambda, or lambda is given by velocity by V. V is equal to nu lambda. This lambda is simply velocity by frequency. Velocity is this much, frequency is this much, divide these two, you get this value. A transverse harmonic wave on a string is described by this equation. Yx comma t is 3 sine 36t plus 0.018x plus pi by 4. This x and y, they are in centimeter and time in second. So the positive direction of x is from left to right. The question is like this: is this traveling wave or a stationary wave? First of all, if it is a traveling, what are the speed and directions of its propagation? What is amplitude and frequency? What is the initial phase at the origin? And what is the least distance between two successive crests in the wave? First is, these are the answers we are going to give you, how we came across all these. This is just for your, just to have a look. Now see, first of all, we have to compare this with the original, or the you can say the proper equation form. The equation of progressive wave traveling from left to right is given by the displacement function yx comma t is a sine omega t plus kx plus phi. Now let us equate. A is what? 3.0. Sine is sine. Omega t. So omega is what? 36. Kx. This is k, 0.018. Phi is what? Pi by 4. So when we compare this equation, we find that this is actually a traveling equation which is propagating from left to right. And when we compare this, we found that omega is 36, k is 0.018. Now we know the relationship, that is V equal to, that is omega equal to 2 pi nu, and also this lambda is 2 pi by k, and also V equal to nu lambda. Nu is the frequency. Now let us use this. V is omega by 2 pi, and in this place we'll use 2 pi by k. See, omega 2 pi, here we will use this value, here we will use this value. So what velocity becomes? Velocity becomes omega by k. Omega is known to us, we have compared it with the actual equation. K is also known. So this is 2000 centimeter per second. You can convert it into meter per second. Now the speed of the wave we just found out to be 20 meters per second. The amplitude of the given wave, as you compare with the equation, this is amplitude. So amplitude is 3. So now this amplitude, because it is 3, the frequency of the given wave will be what? Frequency, which I just told you about this the omega by 2 pi. Omega is 36 as you compare with the equation, actual equation 2 into pi 2 into 3.14. This is 5.73. Now when you compare these 1 and 2 equation, we also found out that phi is pi by 4. Let me tell you again. What is this phi? Phi is this pi by 4. So here phi is pi by 4. So the distance between two successive crest and trough is what? Is actually the wavelength. Crest or trough, this is lambda, right? So what is the wavelength? K equal to 2 pi by lambda. With this expression we know 2 pi, and this K we can just put the value K as we compared it with the equation. So 2 into 3.14 by K is lambda. This is 3.49 meter. For the wave which we just described in the previous discussion, plot the displacement y versus t graphs for x equal to 0 to 4. What are the shapes of this graph? In which aspect does the oscillatory motion in the traveling wave differ from one point to another? Amplitude, frequency and phase. So this was our equation. All the waves have different phases. The equation is like this. Now at x equal to 0, you just have to put x equal to 0 here. Put x equal to 0. What this will become? Y0 comma t will become, this will become 0. It will be 3.0 sine 36t plus pi by 4. We know that omega is 2 pi by t, which is actually, if you compare it here with omega, this is 36. So omega 2 pi by t is 36. So 2 pi by t is 36. What is the t then? It is pi by 8 second. So when we plot the y versus t, we have different values of t you have to give in this equation. So when you put t equal to 0, you get y equal to 3 root 2 by 2. As I said, you just have to put different t values in order to get this y. So when we are putting different t values, we are getting different y. And for x equal to 0, x equal to 2 and x equal to 4, the phases of these three waves will get changed. How? First you have to plot this t with y. Say for t equal to 0, from at t equal to 0, what is y? 3 root 2 by 2. So this is 3 root 2 by 2. At t equal to t by 8, if this is t by 8, you have to put y equal to 3. So what is 3? Here. This is the point. This is how you make the graph. So for all these, this is for 1, we have to find it for x equal to 2, x equal to 0, 0, 2 and 4. So there will be three waves like this. So phase of three waves will get changed. Why? Because the amplitude and frequency are invariant of any change in x. So the yt plots of these three waves are shown like this. I hope you got the idea. You have to do it for x equal to 0 first, then x equal to 2. So firstly this red will come. For x equal to 2, this second will come. X equal to 4, the third will come. And you have to take the x-axis like this, t by 8, 2t by 8, 3t by 8, and the y, of course, you can take any 1, 2, 3 divisions. For the traveling harmonic wave, y x comma t is given by this. So where this x and y are in centimeter and t is in second, we have to calculate the phase difference between the oscillatory motion of 2 points which are separated off by this and this. So the equation is like this: y equal to 2.0 cos 2 pi 10t minus 0.0080x plus 0.35. This equation is what we have written. Now this is the equation which we can write this in certain form. See, this is cos 2 pi, multiply 2 pi inside, 2 pi inside and 2 pi inside. So we can get, because we don't want this 2 pi outside, let us it be inside. This propagation constant k is what? This k is this one, 0.0. When we compare it with the a cos kx, this omega t minus kx plus pi. So when we compare it, k becomes 0.0160 pi, this one. And when you compare the amplitude, see, the amplitude is 2. Amplitude is also known to us. And then angular frequency omega is of course 220 pi. Omega is this 20 pi. This is omega 20 pi. And the phase difference is given by what? Phase difference is simply k into x or 2 pi by lambda. If you take x equal to 4 meter, or you can take it as centimeter, 400 centimeter, the phi will be given by what? You just have to place the value. K is known to us, x is 400. For 0.5, again, this is the k value, put 50 here in centimeters. So you get these two phi. Now for x equal to lambda by 2, if x is lambda by 2, then what will be your phi? 2 pi by lambda into lambda by 2. Okay, 2 pi by lambda and lambda by 2, which gives you pi radian. For x equal to 3 pi by 4, what will be phi? Again 2 pi by lambda into 3 pi by 4. 3 lambda by 4, lambda cancels. It gives you 3 to the 6, 6 pi by 4, which is 1.5 pi radian. This is how it gets. The transverse displacement of a string which is clamped at its both end is given like this. 5 y x comma t is given like this, where x and y are in meter and t is in second. The length of the string is 1.5 meter. Mass is given as 3.0 into 10 to the power minus 2 kg. You have to answer certain thing. Does the function represent a traveling wave or a stationary wave? You have to interpret the wave as a superposition of two waves which are traveling in opposite directions. And what is the wavelength, the frequency, the speed of each wave? You have to determine the tension in the string as well. See, the general form of any stationary equation is given by a displacement function yx comma t is 2a k sine kx cos omega t. If you see, these two are matching somewhat, so the equation is similar to this equation. Now we compare. This 2a is equal to 0.06, k is equal to 2 by 3, omega is equal to 120 pi. So everything is being known. If we compare, the given function represents a stationary wave, and a wave which is traveling in positive x direction is given by what? Y1 a sine omega t minus kx. We know about this. You learned in theory. So which is the wave which is traveling along a negative direction will be what? Minus a sine omega t plus kx. So this is y1 and this is y2. So y2 is given by this. So if you want to find out the superposition, you add y1 with y2, this term with this term. So it gives you a sine omega t minus kx minus a sine omega t plus kx. So when we take a common and sine a minus this sine, you can expand it also, sine a minus b. So sine a minus b and sine a plus b, you have to expand it. Something gets cancelled, things will be cancelled, only this will be remaining, 2a sine kx or cos omega t, which is essentially k. You can write, we know that k is nothing but 2 pi by lambda. You can represent k by 2 pi by lambda. Omega, we know it is 2 pi into frequency, so you can write 2 pi frequency. So the transverse displacement is this equation. Now we are comparing. This 2 pi by lambda is given by 2 pi by 3. Compare it. The wavelength easily can be computed, right? The wavelength can be computed, and when we compare this 2 pi frequency, 2 pi nu by 120 pi, if you compare it, the v becomes pi cancel, 2 divided by 120 is 60, so v is means frequency is 60 hertz. We know v equal to n lambda or nu lambda. We can find out the velocity, which is 60 into 3, which is this one into this one, because lambda is 3, we found out from here. So this is 180 meter per second. Now the velocity of transfer wave which is traveling in a string, we know it is given by under root t by mu. Now velocity is known to us, 180. The mass is also given in the question. The length is also given in the question. The mass per unit length is given by m by l. We have to find out m by l. M is also given, L by is also given. Divide these two, you get mass per unit length, that is mu. Now T is the tension, and we have to find out the tension. Let us square these two sides, means V square and this square. So you get V square equal to T by mu. You have to find out T, so take mu here. So V square into mu. V is what? V square. This is 180. 180 whole square. This is velocity. And mu is what? We just found out this value. Multiply these two, you get tension as 648 Newton. For the wave on a string, which is described in exercise 15.11, that is the question 15.11, do all the points on the string oscillate with the same frequency, phase, amplitude? You have to explain your answer. And what is the amplitude of a point this meter away from one end? The answer is something like this. Then we'll give the explanation first, then you'll understand what is happening here. First is all points or all the points on the string will oscillate with same frequency only at the nodes where the frequency is 0. So at the nodes the frequency will be 0. Otherwise all the points on the string are going to oscillate with the same frequency. Then the second thing which is being sought here is phase and then amplitude. So all the points in any vibrating loop, they have same phase, only except the nodes. And third is, all the points in any vibrating loop have different amplitudes of vibration. You can just check here. You just draw and you'll see that what is happening. At every point, this point amplitude is different, this point amplitude is different. Okay. Then the equation, this we got it from 15.11, the question or exercise. Here, if you put, because the question is given, what is the amplitude of point this meter away from one end? So we have to find the amplitude when x is this one, 0.375. So the given equation was this, yx comma t was this. So let us put this x as 0.375 and t equal to 0. So when we put t equal to 0, this becomes 0, cos 0 is 1. When we put x equal to 0.375 here, it becomes 0.25 pi, or cos 0 is of course 1. So we can find out the value. This is nothing but sin pi by 4, which is 1 by root 2. So 0.06 into 1 by root 2 is 0.042. Given below, these are some functions of x and t to represent the displacement. This is the displacement with respect to x and t. Now these are transverse as well as longitudinal. We have to state which of these represent a traveling wave and which of these are stationary wave, or none of these are either traveling wave or stationary wave. First one will come here. See, this equation represents a stationary wave. Why? Because the harmonics kx and omega t, this one and this one, means kx and omega t, they appear separately, and this is only possible when we are talking about stationary wave. In this case, y equal to 2 under root x minus vt. This equation has no harmonic form, so this is neither a traveling wave nor a stationary wave, so neither of them. And this one is our stationary wave. Now here we have y equal to 3 sin 5x minus 0.5t plus 4 cos 5x minus 0.5t. In this equation, this is representing a traveling wave, because the kx, this one, and omega t, kx omega t, these are in the combination, means kx minus omega t. Here also it's kx minus omega t form. Here k is 5x, omega is 0.5. So this equation is a traveling wave equation. How about this one, y equal to cos x sin t plus cos 2x sin 2t. This equation is a stationary wave. Why? Same discussion, because the harmonic terms, this kx and omega t, they, in this also kx and omega t, they are occurring, or they are appearing separately. This equation actually represents the superposition of these two stationary waves, this one and this one. A wire stretched between two rigid supports vibrates in its fundamental mode with a frequency of this much. This is the frequency. The mass of the wire is also given, and its linear mass density is also given. What is the speed of transverse waves on the string? Speed of transverse wave we have to find out, and the tension in the string we have to find out. So the mass of the wire is given this much. The linear mass density, which is, we know how to find this mu, which is mass per unit length, and this is given here, kg per meter. So this is also given here, mu is given here, and the frequency is also given 45. So frequency is given. Now how to find out the length? You can take length here and divide m by mu. So if you divide m by mu, mass is given to us, mu is also given to us. So mass by mu is your length 0.875. This is the length of the wire. In this case, the wavelength of the stationary wave, which is lambda, is related to the length of the wire by what relation? In this particular case, we have lambda equal to 2L by N. What is N here? This is the number of nodes in the wire. So for fundamental node, we have to put N equal to 1. So when we put N equal to 1 in this equation, N equal to 1, what we get? Lambda N equal to 1, you get lambda equal to 2L. So lambda equal to 2L. Easily you can find out lambda because L is known to us. We just found out 2 into 0.875, which is 1.75 meter. Now, what is the speed? We know V equal to mu lambda. This is frequency, this is wavelength. Frequency is known to us 45. Lambda also we just found out. Put it here. The speed is of the transverse wave is this much. We also know that V is given by under root T by mu. In order to find T, square this and multiply with this. So T is V, this mu square, V square mu. Velocity we have found out, mu we already know. Multiply these two, you get the tension produced in the string. A meter long tube open at one end with a movable piston at other end. It shows the resonance with a fixed frequency source. The tuning force of frequency this much and the tube length this much or this much. Estimate the speed of sound in air at the temperature of the experiment. The edge effect may be neglected. How we are going to proceed with this? First is, we will write the frequency. This is the frequency of the tuning force. You see, this given pipe is attached with a piston at one end. So it is going to behave as a pipe with one end being closed because of this reason and other with open end. So this will be closed and this side will be open as you see here. And this kind of situation, we know, we have seen in theory that this will produce odd harmonics. This is going to produce odd harmonics. So what will be the fundamental node in this closed pipe, which is given by this L1 is given by what? Lambda by 4. We know about this. So L1 will be lambda by 4. L1 is given as 25.5. This is centimeter. Convert it into meter. And this lambda will be 4 into L1. This, see, L1 is lambda by 4. What will be lambda? Take 4 here. Lambda will be 4L1. So 4 into L1, L1 is this much. So 4 into 0.255, which is 1.02 meter. Now we can easily find out the speed also. Speed is frequency into wavelength. The frequency is given also. And the wavelength also we found out. Multiply these two. We get 346.8 meter per second. This is the speed of sound. Now a steel rod which is 100 centimeter long is clamped at its middle. The fundamental frequency of longitudinal vibration of the rod is given to be this much. What is the speed of sound in steel? First of all, the length is given as 100 centimeter, which is evaluated as 1 meter. This is 2.53 kilohertz. K is for 10 to the power 3. So this is 2.53 into 10 to the power 3 hertz. So when we have a rod, see, this is a rod which is clamped at the middle. This is clamped at the middle. That means here you will find that a node will be formed. So the fundamental node of vibration, mode of vibration of the rod, the node is formed at the middle, this point, and antinodes are found at the end. So what is the situation here? From here to here we know it is lambda by 4. From this point to this point it is lambda by 4. When you add these two, lambda by 4, from this point to this point, this is lambda by 4 plus lambda by 4, which is equal to lambda by 2. So L becomes lambda by 2. What will be lambda? L into 2. So lambda becomes 2L. And what is this length? 1 meter. Put length equal to 1 meter, you get 2 meter. Now we all know V equal to nu lambda. Nu is the frequency. We are going to use this frequency. Lambda we just found out 2. Put it here. Multiply them. This is the velocity. A pipe 20 centimeter long is closed at one end. With harmonic mode of the pipe is resonantly excited by 430 hertz source. Will the same source be in resonance with the pipe if both ends are open? The speed of sound in air has to be taken this much. See, the answer is, it should be first fundamental, the second part is no. How? Let us see. We'll write whatever is given to us. The length of the pipe is given to us, which is 20 centimeter. Length is 20 centimeter, so just divide it by 100, you get it in meter. What is the source frequency? The source frequency is simply the nth normal mode of frequency, that is, we call it as Vn. So the harmonic mode of the pipe is resonantly excited by this much frequency of the source, which is the source frequency, nth normal mode. So we can write it as Vn equal to 430 Hertz. Now in a closed pipe, we know that the nth normal, this much normal mode of frequency is given by what? There is a relationship. Vn is given by 2n minus 1 V by 4n. This equation we know. Vn, as I said, we took it as 430. 2n minus 1, let it be like this. V is our speed, 340, and 4 is 4. Length is 0.2 meter. Put it here. We have to find n. I hope you'll be able to find n. N comes to be 1, near about 1. Now, the first mode of n equal to 1. So the first mode of vibration frequency is resonantly excited by the given source. This is not known to us. So in a pipe open at both ends, what will be the nth mode of vibration frequency? This also we know, we have seen in the theory that Vn is given by n into V by 2n. Basically it is equal to n V by 2n. So we have to find out this n. Take 2l here, divide by V. So 2l into Vn by V. This all we know. 2 we know. 0.2 we know because length is 0.2. This Vn is 430. And of course V is the 340. This is 0.5. So since the value n has come 0.5, which is equal to half, so the number, and we know that since the number of mode of observation n, it has to be an integer, this given source does not produce a resonant vibration in open pipe because half or 0.5 is not an integer. Two sitars, the sitar is a musical instrument. A and B playing the note ga, sa re ga ma pa dha ni sa. So ga is being played. These are slightly out of tune and they produce beats of frequency 6 Hertz. The tension in the string A is slightly reduced and the beat frequency is found to reduce by 3 Hertz. The original frequency of A is 324 Hertz. What is the frequency of B? So here, the frequency of string A, FA, is 324 Hertz. The frequency of string B, we don't know, we have to find it. But the beat frequency is given 6 Hertz. See, it is given as 6 Hertz. Now, we know how to formulate the beat frequency. Beat frequency is given by n equal to FA plus minus FB. That means n is the frequency, which is 6. So we'll use this. F is known to us 324 and plus minus FB. So once you will use plus sign, the next time you will use the minus sign. So what will be FB? One time it will be 330, the other time it will be 380. So 330 and 318 has come. Now, since we have to answer the other part also, the frequency decreases with decrease in the tension in a string. Why? Because the frequency is directly proportional to the square root of the tension. Frequency is directly proportional to the square of the tension. So frequency will decrease with decrease in the tension, frequency will increase with increase in tension. So V is directly proportional to under root T. That is why the beat frequency cannot be 330 Hertz. So it has to be 318 Hertz. This is the explanation. Explain why or how in a sound wave a displacement node is a pressure in the node and vice versa. See, a node is where the amplitude of vibration is minimum. like this, like this. Okay. So this is a node, these are the antinodes. So here at this point, the amplitude of vibration is minimum and the pressure is maximum. Pressure is max. But if we talk about the antinode, these are the point. Here the amplitude of vibration is maximum. A is max here. And P is not max, but P is minimum. That is why in a sound wave, we can say that displacement node is nothing but a pressure node and vice versa. This is first explanation. Next is BAT can ascertain distances, directions, nature, sizes of the optical without even having eyes. We don't have the proper way, the vision we have. So BAT emits high frequency ultrasonic sound waves. They are capable of sending high frequency ultrasonic sound waves. So these waves, they are reflected back toward them by obstacles. Like if this is a bat, it sends the waves, and by obstructing, if there is any say body or obstacle, this will reach again back. So bat now receive the reflected wave, and now he or she estimates the distance, direction, nature, and size of the obstacle with the help of its brain senses. Next is this one. A violin note and a sitar note may have the same frequency, but we can distinguish between the two notes. How? See, the overtones which are produced by sitar and violin, and the strength of these overtones itself and the strength of overtones, these are different. So one can distinguish the notes produced by sitar and violin even if they have same frequency of vibration. And there is one more thing which is called timbre. Timbre helps us to differentiate the sound. Next is solid can support both longitudinal and transverse wave, but only longitudinal wave can propagate in gases. So the reason here, we'll try to answer this one, right? See, both these solids, they have shear modulus. What they have? Shear modulus. So they can sustain the shearing stress. Since these fluids, they do not have any different shape, they yield to shearing stress. When we are talking about the propagation of this transverse wave, the propagation of transverse wave is such that it will produce shearing stress in the medium, and the propagation of such wave is possible therefore in solid because they have shear modulus, but not in gases. Both solid and liquids, they have bulk modulus B respective. Now they can sustain the compressive stress. That is why the longitudinal waves here, they can propagate either in solids or in fluids. The shape of the pulse get distorted during propagation in a dispersive medium. So a pulse is what? This is nothing but a combination of waves having different lambda wavelength. These waves, they travel in dispersive medium with different velocities, and this depends on the nature of the medium also. So the result is the distortion of the shape of the wave pulse. A train standing at the outer signal of a railway station, it blows a whistle, and the whistle of frequency 400 Hz in still air. What is the frequency of the whistle for a platform observer when the train? First, it approaches the platform with the speed, recedes the platform with the speed, and what is the speed of sound in each case? The speed of sound in still air has to be taken 340 meter per second. So the idea here is frequency of whistle is V, 400 Hz, which is given in the question. Speed of sound we have to use 340, and the speed of train, this one, is 10 meter per second. So when the train is approaching the platform, that means the observer is at rest. We know the V dash, the apparent frequency will be V by V minus Vs into frequency. All these values are known to us, just put it here. You get 412 Hertz. Now when the train recedes from the platform, that is the observer is now at, from the observer which is at rest, this gives you V by V plus Vs into frequency. So all these values are known to us. Put it here, we get 389 Hertz. In the third one, what is the speed of sound in each case? See, the speed of sound in each case, it never changes. The speed will remain same. The frequency only changes. A train standing in a station yard, it blows a whistle of frequency this one. So this already we have seen. See, it's a kind of question which matches with the question here. So we'll take a look here because the formulation is somewhat different. So let us see. It is somewhat nearer to the previous one. So a train standing in a station yard, it blows a whistle with frequency this one. Now we have a wind here. So the wind starts blowing in the direction from the yard to the station with a speed of this much. So there is a wind speed also. What are the frequency, wavelength, speed of sound for an observer standing at the station's platform? Also, is the situation exactly identical to the case where the air is still and the observer runs towards the yard at a speed of this much? The speed of sound in still air, this can be taken this much. So this is the answer actually, and we'll see how we got this answer. You must remember these underlined values because we are going to use it directly. So the frequency of sound produced by the whistle is also given, speed of sound is given, velocity of wind is given. Now, there is no relative motion between the source and the observer. So the frequency of sound which is heard by the observer will be exactly same as that is being produced by the source. So it will be 400 Hertz only. One thing is clear. Now there is a wind. So our wind is blowing towards the observer. The effective speed of sound will increase by what? 10 units because the wind is also there. We have to add it. So the effective speed VE will be 340 plus this 10. 10 is of wind. So this becomes 350. Now what will be the wavelength of the sound which is heard by the observer? We know the wavelength is given by this V effective by the frequency 350 by this frequency 400 Hertz. This is 0.875 meter. And if we have a running observer, we know that the velocity of observer is given as 10 meter per second. Now the observer is moving where? It is moving towards the source. And because of this scenario, the relative motion of the source and the observer, there is a change in frequency. This V dash is given by V plus V0 by V into this frequency. So 340 plus 10 by 340 into 400, this gives you 411.76. And since the air is still here, the effective sound will be what? 340 plus 0, air is still here, it will be 340 meter per second. The source is at rest, so the wavelength of the sound is not going to change. Lambda will remain as 0.875. So these two given situations, they are not exactly identical, they are different. So these are the question and answer on this topic. Thank you so much and take care of yourself.